Hi everybody, so in this video we're going to begin with Chapter 10, Differential Calculus 2. So these are the learning objectives for the chapter, and by the end of the chapter you should be familiar with the following. Finding the derivative of a composite function. Finding the derivative of a function that is in the form of product or quotient. So remember, this is multiplication and this is division. Finding the derivative of exponential and logarithmic functions. And finally, solving problems requiring solutions where there's an optimum, that is, a maximum or a minimum. This is called optimization. So specifically, we're going to be doing 10.1, which is derivatives of exponential and logarithmic functions. And first, we're going to see the derivative of the exponential function, y equals e to the x. So one of the interesting things about Euler's number is the fact that Euler's number to the x, or the derivative of Euler's number to the x, is equal to Euler's number to the x. And that's one of these interesting things about this artificial number, man-made number, is the fact that you can find the slope of the curve or the slope of the tangent on the curve of e to the x by plugging the x coordinate in the function itself. And that will be the slope of the line at that point of tangency. So next we're going to see a summary of differentiation rules, and these are some derivatives that are very common. The first one is the power rule that we have right here. Remember, it's just if you have x to the n, the derivative would be multiplying by n and then subtracting 1 from the exponent. We have that the derivative of sine is cosine, that the derivative of cosine is negative sine, the derivative of Euler's number to the x is Euler's number to the x. And then finally, we have to know the fact that the derivative of the natural logarithm of x is simply going to be 1 over x. Okay, so next we're going to do example 10.1. And it says differentiate each of the following functions. So for a, we have f of x is equal to 5 minus 2 times e to the x. So the derivative of f of the x is going to be the differentiation of 5 and the differentiation of 2 times Euler's number. So first we're going to differentiate 5 minus 2 times the differentiation of Euler's number to the x. So notice that the differentiation of 5, because it's a constant, is just going to be 0. Minus 2 times the differentiation of Euler's number to the x, and that's just going to be Euler's number to the x. And then we're left with the expression minus 2 times Euler's number to the x. So for b, they want us to differentiate g of x is equal to natural logarithm of x over 2. Now notice that we can rewrite this as 1/2 times the natural logarithm of x. And then we can do the derivative. And that would just be 1/2 times the differentiation of the natural logarithm of x. And this would just be 1/2 times 1 over x, or 1 over 2x. And then finally, we have example C that says y equals 6 minus natural logarithm of e to the 3 over x. Now notice that we can rewrite this equation because this is a logarithm. Remember that rule where you can rewrite this as 6 minus, and I'm going to use a parenthesis here, natural logarithm of Euler's number to the 3 minus, remember that we can change a division into a subtraction of logarithm, so minus natural logarithm of x. And then this is going to equal 6 minus, and this is just 3, right? Because the natural logarithm of e to the power of 3 is just 3. Minus natural logarithm of x, and this finally is going to be 3 minus natural logarithm of x. Okay, so we want to differentiate this. So the derivative of this is going to equal the differentiation of the constant 3 minus the differentiation of the natural logarithm of x. But this is just 0, right? Any constant, the derivative of any constant is 0. So this is going to be 0 minus 1 over x. Oh, I made a mistake here with the sign. This should be plus because minus times minus is plus. So 0 plus natural logarithm of x, and the derivative of that is 1 over x. So that means that the solution to this would be 1 over x. So next we have example 10.2, and they say find the equation of the line tangent to each function at the specified value of x. Express the equation exactly. So whenever you see exactly, that means don't use decimals. It means use Euler's number or the square roots or the exact value, because those are irrationals, and the only way to express them in an exact manner is leaving them in that form. So letter A says y equals e to the x plus 1, and they want us to find the point of tangency at x, or the equation of the tangent line at x equals 1. First, we need the y coordinate, right? So y of 1 is just going to equal e to the 1 plus 1, and that's just e plus 1. That means that the coordinate we need, or the point of tangency, is going to be 1 comma e plus 1. Now we need to find the derivative of this, but that's easy, right? We know that the derivative will just be Euler's number. And then at 1, we will find the slope of the tangent line. So we plug in 1, and we're just going to get Euler's number. So remember that the point slope formula says y minus y1 is equal to m, the slope, times x minus x1. So we use this to find the equation of the tangent line. So it's going to be y minus, and we have to use parentheses here, e plus 1 is equal to the slope, which was e, we found that here, times x minus x1, which is 1 right there. And then all we have to do is expand and rearrange this. So this is going to be y minus e minus 1 is equal to ex minus e. So notice that this and this will cancel out, and we're going to end up with y is equal to e times x plus 1. And then last but not least on this video is part B of example 10.2. And the equation is y equals natural logarithm of x, and they want us to find the equation of the tangent line at x equals 4. So that means that the coordinate is simply going to be 4 comma natural logarithm of 4. And we want to leave it in this way because they want us to find the exact value, right? They want us to express the equation exactly. Okay, now we need to find the derivative. The derivative of natural logarithm is simply 1 over x, and then we need to plug in 4 in order to find the slope of the tangent line. So that's going to be 1/4. And we're ready to use the point slope formula. So it's going to be y minus natural logarithm of 4 is equal to 1/4 times x minus 4. And then all we have to do is expand and rearrange. So we're going to get y minus natural logarithm of 4 is equal to 1/4 x minus 1. And then we're practically done because this will just be y is equal to 1/4 x minus 1 plus natural logarithm of 4. And we leave it like that because they want us to express the equation exactly.